Today we'll talk about metal additive manufacturing and specifically binder jetting as a way to mass produce parts and compare that against conventional methods to produce parts. We'll talk a little bit about the pros and cons. So first, just a little context. The mission of Desktop Metalware, 5-year-old, 6-year-old company at this point, it's to make industrial 3D printing a reality for engineers, designers, and manufacturers. And what that means is engineers, designers, so relatively low volume kind of printing solutions, and in manufacturing, mass production of metal parts. The promise and the goal we set for ourselves is to develop cost competitive, high speed, high quality printing solutions, so you can actually print the parts that billions of people can then use. Today, there's hundreds of organizations around the world across a broad range of industries relying on us for their metal 3D printing, and you'll recognize some of the logos here, and many you may not, and that's kind of the point. Metal additive manufacturing is now at a point where relatively small and mid-sized companies, it's entirely accessible to them in terms of both cost and what it takes to set up and operate. The range of our printing solution starts from the Studio System, which is world's first and only office-friendly way to print parts, and then move into the Shop System for turnkey batch production of parts, and then our production system, which are the fastest ways to you can produce literally 100+ tons of metal parts per year with one of those systems. The Shop System, as I said, is for batch production of dense customer-ready parts. I'll share in a little bit some details about how it works and recommend or propose some selection criteria when you're looking at metal additive solutions. There are a number of good solutions out there, so it means you got to choose carefully and see what's right for you. But the basic premise of it is that it's a scalable and a cost-effective way to get started producing one or more entire build boxes of parts per day, so you can make tens or hundreds of parts per day. It's a turnkey system, so all the parameters, all the aspects of the systems have been tuned, and you can do this up to 10 times faster than laser powder bed fusion kind of systems. And then we have the production system, which is for truly high-speed mass production of metal parts when you literally need to produce hundreds of thousands or millions of parts per year. This replaces factories full of CNC machines. And we'll distribute the slides afterwards, so no need to write anything down or do screen capture. But in a nutshell, here's a few of the key parameters on the basis of which to at least select amongst our systems. And that's both in terms of how many parts do you need, kind of per week or per year, the size of the parts, so the build box changes, and then what are the key costs and kind of materials capabilities of the parts. There are trade-offs where you can trade off larger capital equipment costs for a much lower part cost. So before we dive into metal additive, let's just review the state of things in conventional manufacturing. So there's a few important challenges being faced by conventional manufacturing methods today. So one set of challenges is around product innovation. So there are, due to the manufacturing capabilities of the CNC tools or casting solutions and others, there's limitations with respect to geometry, and there are limits to customization, in particular when you're talking about tooling costs. So often for one particular kind of part, you might need to produce tooling that when this part changes, this adapter changes somewhat, you got to make tooling from scratch. So custom parts or customizing, even mass customization, or even just a product family variation becomes quite difficult. So that's customization. And then there's limitations to process innovation. If you think about time to market, there are lead times associated with producing tooling that can be months to stand up a manufacturing line. Because tooling is a relatively large fixed expense, it's got to be amortized across a large number of parts, or it can be not very cost effective. Inventory, if you think about, I mean, over the last couple of years, exacerbated by the pandemic, but even before then, you think about parts are often produced in one part of the world, then they're shipped, stored, distributed across the world. So it's really not trivial. By the time the part reaches you, it might be 6 months or more from the time it was actually manufactured. And so reducing this, compressing this is a key thing. And finally, cost, both in terms of part cost and the labor, the labor and the time it takes to do post-processing or machining at scale can be quite expensive, quite prohibitive. These are all the challenges that make additive manufacturing an exciting alternative. With respect to geometry, with additive manufacturing, you have a lot less geometric constraints. So you don't have to design a part for the manufacturing process. You can design it much closer to what you might actually need. So just like you think about it in nature, a tree limb grows and there's really fibers just where they need to be. The limb is stronger or the limb is thicker where it needs to be due to the stresses. And if it's just towards the end of the branch, if it's only supporting a leaf, it can be a lot thinner. And so you can remove material based on the functional requirements. You can do that with design and then realize those designs with additive manufacturing. The other thing is, because there's no tooling, you can do mass customization trivially. It's very easy to make an entire build box where every single part, whether it's, let's say it's a custom shift handle for an automobile, everyone can be different, and it's just as easy, just as fast to produce that. And with respect to process innovation, you can dramatically compress. You can literally design a part this morning and be printing it this afternoon. And so time to market, both in terms of prototypes, batch production, pilot production, qualifying new products, dramatically compressed. And so now you can do market testing and all the things that you used to do in a serial fashion or in much more limited way when you have to deal with processes that require tooling. Now a lot of that can be compressed. The volumes, the volumes really are, it's cost effective whether once you have a 3D printing press, producing 100 parts is just as cost effective as producing 1 million. And so you can really choose to scale by buying the printing presses, and part economics don't get any worse. With respect to inventory, imagine what it means to have this notion of digital inventory of one, where you're printing just the parts you need on demand. And finally, with a lot of these processes with additive manufacturing, you can produce near net shaped parts. Just looking around, whether it's, let's say, this part for a motorcycle turbo, or this kind of jewelry pieces, you can produce near net shaped parts that require a lot less post-processing and lower per piece operator kind of cost. So that's really the key benefits in terms of both the product aspect and what it does for your business and supply chain, that additive even has a shot. And now, because a bunch of planets have lined up around this, the additive manufacturing industry is at an inflection point. Additive manufacturing has been around since the 80s. But for decades, it's been relegated to prototypes, sometimes functional prototypes, but relatively low volume kind of applications, jigs, fixtures, tooling, and some functional prototype. Whereas in manufacturing, it's all about the end use parts. So finally, because of a bunch of planets have lined up in terms of materials, in terms of printing techniques, in terms of robotics capabilities, a bunch of these things have lined up to make mass production via additive a reality. So the key things that have prevented additive manufacturing from kind of taking over, or at least playing a serious role in mass production of end-use parts, is this surface finish, the accuracy of the parts, the material properties, the speed, and the cost. Those have all been barriers to overcome. The good news is, for a bunch of reasons, those barriers, we argue, and our early adopters would argue as well, have been overcome for many applications, is with binder jetting. And so what we see, what our customers are seeing, is that additive manufacturing 2.0, this second stage of adoption of additive manufacturing, is driven by two things. One is accessibility, how easy it is to stand up a new capability and be able to produce the parts in high volume. And so that means everything in terms of finish, material properties, the accuracy, the cost, the speed, they're finally there. This wasn't the case as recently as 3 or 5 years ago. Now it's here. And so we'll review kind of pretty quickly a whole bunch of application examples. But first I want to spend a little bit on how the stuff works, like what's new versus what's been around, and how this new approach compares with some of the conventional manufacturing methods. So first of all, what is binder jetting and metal additive manufacturing? Well, what we and a lot of the competing alternatives have done is create a way to produce metal parts via standing on the shoulders of metal injection molding. MIM, metal injection molding, is a powder metallurgy process that really enables a lot of shape complexity. It's useful to understand this because this is the foundation of a lot of cost-effective metal additive manufacturing methods. MIM powders, so this is a process that's been around for at least 60 years, and it's widely accepted and widely validated. So this approach of using metal injection molding is established, supported by over 100 different alloys. They're standard. So we're really, we and our competitors that are involved with metal additive manufacturing are really standing on the shoulders of all of the development that's taken place in MIM over the last several decades. How it works is as follows. You take the metal powder, mix it with a polymer binder to create the feedstock. And then the next step is this feedstock is injected quite similar to how you might injection mold plastic into molds. It's heat under temperature and pressure. The feedstock melts. Really what melts is the polymer. The metal powder comes along for the ride. It's injected into forms. And then that's how you create the shape. After a solvent debind that eliminates some of the binder, that shape, that part, it's like you have a sandcastle. That sandcastle, grains of sand, obviously it's not sand, it's metal powder, and it's held together by this temporary glue of the remaining binder that's put into the furnace. And during that sintering, very specific sintering process, the binder that's holding the part together evaporates while the metal powder particles come together through solid state diffusion bonding. And so here's, in a nutshell, how you have powder metallurgy based metal 3D printing. This first row is metal injection molding, and then with our studio system, we create this feedstock as instead created as rods. Now, because they're not powder, they're office friendly, and so you can, with an extrusion based FDM kind of a printer, you can create the shape and then sinter the part. Or with our binder jetting solutions, which is really the focus of today's talk, it's create the powders, take the powders from largely from the metal injection molding industry, properly characterized and specified. So there's not any powder, but we've tuned the powders, tuned the binders, and then with a binder jetting printer and a furnace, we create the parts. So that's a little bit about how the printing process works. I want to jump for a second to let's put the focus on traditional manufacturing, whether it's machining or casting or powder metallurgy, which is really, these are the three most common ways to create a lot of the metal parts we see around us. The challenge with every one of them is there's some amount of setup and tooling required. With machining, it might be developing the processes, the programming, the soft jaws, the multiple steps, some operator training. There's a fair bit of, whether it's machining or casting or powder metallurgy, fair bit of non-recurring, custom, tailored to the kinds of parts you're making, engineering costs and labor, and tooling costs associated with setting up a production line. And for all those reasons, the result is it takes months, easily months, to bring a production line up. And as a result, there's often less design iteration, and you might inevitably, we all make some sacrifices with respect to the design. Maybe there's not as much of an opportunity to optimize the design to make it just that much stronger, just that much more aesthetically pleasing. And so there are some sacrifices. And for all of these methods, you really need minimum quantities. And sometimes that's tens of thousands. Sometimes it's a little bit less. Sometimes it's even more to really justify spending, could be easily tens or hundreds of thousands of dollars or even more for tooling. And so what does that mean in terms of setup processes? So for machining, I won't go into all of the steps that are kind of outlined in the box on the right, but there is prep and iteration, and it takes several weeks to get to volume production. With casting, it's somewhat different steps, but it can easily take 4 months or so. And with metal injection molding, it's even more. It could be 5 months, and it takes, and really there's minimum quantity cutoffs where below could be 10,000 or 20,000 parts. It really doesn't even make sense to metal injection mold the parts. And so then ask yourself, the design just changed. I now have, instead of this part with, I don't know if you can see the, right in there, the teeth. We'll have a close-up of this part later, but if the pitch changes or there's another relatively minor change, the process starts over. There's largely no transfer benefit from the fact that you made a previous iteration. Instead, with binder jetting, there is a process, there's some prep, there's some pilot production, but really within 1 to 2 weeks, you have a tuned process that's able to be produced, turned on, and if you want to scale it, run it second shift, third shift, run it on weekends, buy the second printer and scale accordingly. So binder jetting is just a game changer with respect to conventional manufacturing processes. So you can see a lot of different parts being made, parts relatively small, parts relatively large, could be complex gears, could be whole assemblies of gears. I'll give a few examples. So this is an example of a parking shift bracket. I have one here in the home office, but you see on the production system, the part is less than $5. This part would normally be produced via a relatively complex probably casting operation with a bunch of secondary operations, because there's some complex bosses in here. You can't produce it via stamping on a progressive die. So really you'd need to cast and then post-process this part. With 3D printing, you can manufacture boxes and build boxes of them per day. You can make hundreds of thousands per year. Another example, a part for a stator motor. Again, in one build on the production system, you can just make several hundred of them, another several 100,000 per year. Here's that power steering joint I was showing. Again, on the production system, it's just about $2, and you can make not quite 1,000, but over 500 of them per build, so over 1 million per year. So on the shop system, here's another example, seatbelt pulley, few dollars, and you can make them. You want to make 10, you want to make 100, you want to make 1,000. Trivial with a shop system. You can make thousands per week. Lock plugs, relatively complex parts. You make 1,000 per build, 9,000 per week. So just another part, fuel swirler. Again, relatively complex parts, not an obvious way Even with metal injection molding, this part would be somewhat tricky to produce because of the veins and the interferences that are involved. So hopefully at this point, made the case that at least some parts may make sense to produce via binder jetting, and in particular via the shop system. By the way, I see there's questions coming up. Love that. I'll jump and answer them in just another couple of minutes. So with a shop system, this is turnkey, not turkey or turnkey metal 3D printing, designed for the machine shops. And that really means it's designed for you. You open the door, you wheel the system in, and it can work right in the environment, fits right into the kind of environment that's present and the kind of labor that's available inside a machine shop. You can, within days, have one of your machinists be totally up to speed on running a metal binder jetting solution. So a couple of words on the shop system. Already mentioned that it's for batch production of fully dense, near net shape, customer ready parts. So for example, these parts that I'm holding up, no post-processing, right out of the furnace, the parts. And so depending on, now you can plate them, you can machine them. If you need a specific surface, kind of either surface finish, there's a lot of different finishing methods available to them. So this one, if you wanted a very smooth finish for whether it's aesthetic or other functional reasons, you can pretty easily do that. There's essentially 3 steps. There's a printing step. There's a depowdering step where, well, let's see. There's a depowdering step where the build box is removed, placed in a powder station where the parts are kind of excavated from the powder. The remaining powder, the loose powder, is removed, recycled, and to be used for the next build, and then the parts, as they're removed from the build box and depowdered, can be sintered. This is the full solution. There is a printer, of course. There's a drying oven that's to give the green parts before they're sintered strength, so that when you're depowdering them, they're even more robust, so you can handle them. You can blow them with the air, compressed air, and have the part not get damaged during that process. Furnace, there's a blender for mixing the virgin powder with a recycled powder. The key features, and really I won't spend a ton on this, but this is kind of a selection guide. If you're evaluating systems, you might want to look at what is the speed, what are the steps involved, and how much process development do I need to do versus it's kind of defined well as a turnkey process. What's the resolution of the print head? What is the resolution of the resulting parts? Is there redundancy so that if an inkjet nozzle is clogged, it doesn't stop my build? What kind of productivity can I get if I'm running it as a build today? How many builds can I do? How many parts can I make per day? How easy is it to do post-processing? And what kind of capability does the print engine have in terms of to achieve the best kind of surface finish? These are all, so these are attributes of the shop system, but really this is a pretty good list of what are the things to look for when you're choosing a binder jetting solution, kind of the basis on which to evaluate them. This is just a few examples from the field of the kinds of parts people are printing. You can make relatively complex parts, small parts, medium parts. I've seen parts that are the size of the entire build box. It's not yet recommended to print as one giant parts. There's still some process development that needs to take place, but it's coming. I remember what the shop system could do 2 years ago, what it could do 1 year ago, 6 months ago. So constantly the team is making upgrades and improvements, refinements, and the scope of the kinds of parts that people can make is dramatically widening, even just over the last several months. There's a few key usage scenarios. All of them are valid. All of them are being used. There's kind of the mixed volume. So all the parts are different per build. Maybe you just want 1 or 2 of a bunch of different parts for prototyping, functional testing. You could do batches with maybe 2, 3, 4 different parts with starting to do some volume, maybe for pilot production. And we've seen kind of mid-volume production with a shop system where you can make hundreds of the same part, whether it's a class ring. This one happens to be gold plated, but printed on the shop system. I don't know how well you can see it. Like I said, this is for a motorcycle turbo with some nice inner features. This would be a really tricky part to produce any other way, trivial with a shop system. And kind of the bottom line is, A, you can reduce costs by eliminating tooling, reducing your tool wear in your shop, reducing the labor per part, of course, reducing the setup costs. Suddenly, if you've no bid some jobs because of the setup costs don't justify making a handful of parts, now it's relatively trivial to produce even one of something. And you can, by producing near-net shaped parts, you can reduce the total number of steps that it takes to manufacture a part. So A, you can reduce costs for existing parts, and 2, you can increase revenue by producing parts that you couldn't produce with geometries that you couldn't produce before, or you can print metals that might be hard to machine, whether it's tool steels or just Inconel or other hard metals. Make smaller jobs economically possible, free up your CNC capacity for other jobs. So for all these different ways, this can A, reduce costs, B, increase revenue. So binder jetting may be a worthwhile thing to look at, and wanted to give a couple examples from the field. So first of all, there's at this point many scores of systems out there since we introduced the shop system at the end of last year. These are some of the customers across a bunch of geographies and application and industry sectors. And I'll give a couple examples. One great example is EAC. EAC is a company in France. It's a leader in metallic ornaments, and they do a lot of luxury kind of goods for a lot of leading brands. And they've turned to additive manufacturing as a way to produce parts that can't be produced in produced designs that can't be produced any other way. So I'm going to show just a couple of these to give you a sense of, so these are very fine parts. The cool thing about this ball, and this is going to be hard to see, but I'm going to try. There's a ball inside a ball here. So that's a geometry that you really can't produce any other way. There's other just relatively complex geometries. And really, additive is becoming kind of a secret weapon for EAC because they can create geometries they couldn't produce before, and the productivity benefits. The current manufacturing methods really required expensive tooling. So now you can produce a lot more in a broader set of parts, and you can literally process many thousands of parts per week, which really changed the game for EAC. I'll show a couple examples. This is just a few examples that they've printed and then finished in a variety of ways. But you see a lot of different, very cool kind of luxury components for, these are some of the parts, and here are some of the parts in context. So this is actually moving joints. This is like a sun with a bunch of planets around. They spin around. So you can make thousands of them per build, over 100,000 parts per week. So just dramatic productivity kind of gains. Previously, at best, you could maybe cast them with a much lower throughput. This is for parts for leatherwork. The parts are printed, then finished and plated, but you can make thousands per week per build, and over 70,000 parts per week. So really a great way to do mass production. And here's that part I was showing earlier. You can kind of see, I think you can kind of see the ball in there. And in general, this is the mixing and matching. Here's the build box, and you can put a whole bunch of different parts. By the way, you can scale them. So you could really do a lot of innovation right with a shop system. You come up with an idea, and that day you're printing it. And you can do designs that are that are unique. It's hollow inside, really complex stuff without needing tooling. And here's another great example. A completely different application example is with a Wall Colmonoy, which is really a leader in materials engineering. They make a lot of engineered components for a broad range of industries, including automotive, aerospace, food production, oil and gas, mining, so heavy industry, a lot of different applications. And what they've turned to with a shop system is they want to be able to produce parts without tooling, without metal injection molding or casting kind of requirements, and be able to, if you think about it, they do a lot of custom work with their customers early on. And so somebody comes to them, they're able to come up with a design and turn it around that week instead of waiting maybe for the first part to be cast several, it could be a couple of months. And so by getting in early and reducing the ideas to practice early, they can really work with their customers to steer the design, to improve the design, and it's a win-win for both Wall Colmonoy and their customers. So be able to cut out tooling and produce complex designs, near-net shape designs in a variety of materials, really a key thing for Wall Colmonoy. Another example, FreeFORM, great contract manufacturer of precision components in a variety of metals, located in Pennsylvania. And MIM tooling, the challenge is this: MIM tooling, and these are experts in MIM, is quite expensive. It can be easily $40,000 or more for a relatively small part, and there's routinely 8 to 12 week kind of lead time to develop and deploy that tooling. And MIM, on top of that, has some geometric limitations, which then requires post machining. With 3D printing, you get the parts in days instead of months, and you can produce a part that's much closer to the net shape. So this is a giant bet that the team at FreeFORM is making. In fact, they're all MIM experts and have MIM in their past, but they're betting their future on additive manufacturing. They're really a 3D printed first kind of innovator. Another example is PGV Oil Tools. So this is a company pretty close to San Antonio, I think, but it's still an hour's ride, but located right in the middle of oil and gas, heavy industry country. They have customers all over, and they produce a lot of different parts that have the following things in common. They're for downhole tools. Those tools are often relatively expensive to produce. They're cast, they're machined, and they have to stock inventory because there's kind of minimum orders for when they do need to produce 50 or 100 of something, even though they might need 4 or 5 this week or 5 or 10 next week. And so the ability to print on demand parts that are much closer to the near net shape is a dramatic improvement for them in terms of for the more complex parts and supply chain kind of challenges, and the parts actually lower cost on a per part basis. So you have a sense of what these are. So these are downhole tools, and then there's on the tool, there's a downhole tool slip that provides friction between this pipe that's lowered into into the downhole. I don't know all the terminology, but basically the big steel pipe through which that might go down a mile, 2 miles for oil, and so these parts provide friction between so that the part it's spring loaded and can stay solidly in one place as it's lowered or raised. And the parts provide, as I said, a frictional hold between what's called the frac plug and the pre-existing pipe. That's the language I should have used. And the parts were prototyped on the studio system to test the various geometries, but once there's a commitment to a particular design, and the designs change pretty frequently, they can 3D print them with a shop system. And because it's important. The final parts need to be metal. If you're going to do functional testing or pilot production, of course, the parts got to actually function. They got to be metal. And so this isn't about, I want to test form and fit. This is, I'm going to do functional testing on 1, then 10, then 100. Here's just some of the parts. Here's the environment in which the shop system was installed. This is Ramon, and he runs the place, comes up with a lot of the designs. Here you can see some of the parts, and there's actually carbide inserts that have been brazed in. Some more of the, so here are the parts printed on the shop system, solid metal, and here they are installed on the downhole tool. Soon we'll get, now these are actually in the ground, a mile or more deep, and soon we'll get some awesome pictures from those field tests and field deployments as well. And the last customer example I'll share is PORAL. So this is a leading supplier of powder metallurgy components. And you kind of see a lot of companies that have expertise in MIM or powder metallurgy. They see that additive manufacturing is coming from and is an innovation on top of powdered metal. So they're some of the earliest to get into additive manufacturing. They provide powder metallurgy components for a lot of very demanding markets: automotive, aerospace, nuclear, chemical, food, etc. And the challenge, like it is for almost every one of these customers, they want to produce parts quicker. They want to be able to eliminate fixturing tooling costs. They want the flexibility, the supply chain flexibility, the compressed lead times. And for all those reasons, they're turning to additive manufacturing, turning to the shop system. The benefits that they've gotten is the design freedom, the ability to serve customers earlier in the design cycle, and of course, elimination of the tooling costs. And so they're really able to produce near net shape parts. Here's a quote from Dennis, the CEO. They can get unprecedented precision, surface quality by combining what the benefits are of 3D printing in terms of freedom of design with the advantages of powdered metallurgy, the quality you get, the repeatability, and by the way, the energy savings. You know, you're not running a gigantic furnace, and you don't have to worry about a giant amount of liquid metal. You're taking powder. So this is a much greener process where you're taking powder and just the parts that need it, raising them just to it's not even the melting temperature, it's the temperature at which there's solid state diffusion bonding between the particles. So it's a greener process, better metallurgy, better near net shape parts.